Okay, so we have a modern optics practice final exam, graduate level. Um, I'm going to go through this rather quickly to get you through it. You'll have this as a reference for practice problems, and you could always pause the video, go back to whatever you want to go back to, and just check over the steps and the answers. Some of the intermediary steps, but the computation are not shown. So let's just go through. Number one, plano convex lens of focal length f is placed at a distance d from a concave spherical mirror of radius r. Paraxial ray starts at distance to the left of the lens. I'm going to read part A, B, and C for this. Construct the full round trip ABCD matrix that just before the lens back to just before the lens. Sorry for misspelling that. B, determine the stability condition for repeated round trips. C, find the self-consistent Gaussian beam waste condition inside the system. Okay, so ray optics and ABCD matrices. We're going to use matrices L equals 1, 0, negative 1 over F1, P of D equals 1D, 0, 1, and M sub R equals 1, 0, negative 2 over R1. Round trip just before the lens is M equals L, P of D, M sub R, M sub R, P of D, L. For stability, absolute value of A plus D over 2 is less than 1. For Gaussian beams, Q prime is A sub Q plus B over C sub Q plus D. And over here we could say a self-consistent cavity mode satisfies Q equals A sub Q plus B over C sub Q plus D. So we could say C sub C Q squared plus quantity D minus A Q minus B equals 0. So we choose the root with positive imaginary part because 1 over Q equals 1 over R sub B minus I lambda over that pi waist squared, or beam radius squared. Okay, so that's number one, and my apologies for the misspelling. Okay, so here, right here, number two. Okay, so for number two, let's see what we have. A thick lens has refractive index n sub I, radius r sub 1, r sub 2. I'm sorry, a thick lens has refractive index n sub 1, radii r sub 1 and r sub 2. And center thickness t, I'll read A, B, C, D, and E. Derive its ray transfer matrix in air. Determine its effective focal length. C, locate its front and back principal planes. And D, explain when the thin lens approximation fails. So, thick lens and principal planes problem. We're going to use refraction and translation matrices at a spherical surface from n sub 1 to n sub 2. We get this, S equals 1, 0, n sub 1 minus n sub 2 over r n sub 2, n sub 1 over n sub 2. The thick lens matrix is this, M equals this S sub 2 P of T S sub 1, with P of T equals 1T 0 1 here for the values inside, if using the Y comma theta convention. And the lens maker formula, 1 over F, that's 1 equals n minus 1 times the quantity 1 over r sub 1 minus 1 over r sub 2 plus quantity n minus 1 times t over n r sub 1 r sub 2. And we could say the thin lens approximation fails when t is not negligible compared with the radii of curvature, focal length, or propagation distances. Okay, so that's number two. Moving along to number three. Okay, so number three. Okay, so we have two monochromatic plane waves of wavelength lambda intersect at angle 2 pi. Their electric field amplitudes are respectively E naught and alpha E naught, with 0 is less than alpha is less than 1. I'm going to read A, B, C, D, and E. Derive the fringe spacing. Derive the fringe visibility. Determine how partial temporal coherence modifies the visibility. and discuss the limit where the optical path difference exceeds the coherence length. So this is an interference with unequal amplitudes type problem. Okay, so here, let E sub 1 equal E naught, e to the I times raised to e to the I times that quantity k sub 1 dot r minus omega t. And then E sub 2 equals alpha E naught e to the I parentheses k sub 2 dot r minus omega t. The intensity is I equals I naught times the quantity 1 plus alpha squared plus 2 alpha cosine delta phi. If the beams cross an angle 2 theta, then we have, we use this, delta k sub x equals 2 k sine theta. This fringe spacing is lambda equals 2 pi over delta k sub x, and that's lambda over 2 sine x. And maximum and minimum intensities are I sub max equals I naught times the quantity 1 plus alpha squared. I sub min equals I naught times the quantity 1 minus alpha squared. Visibility, the visibility I sub max minus I sub min over the sum I sub max, I sub min. That's 2 alpha over 1 plus alpha squared. And with partial coherence here, V equals 2 alpha over 1 plus this alpha squared times the absolute value of G1 of tau. And if the path difference exceeds the coherence length, then that magnitude of G1 approaching 0. So the fringes, they go ahead, they're gone, they disappear. Okay, so that's number 3. Okay, moving along to number 4. Okay, number 4, a Fabry-Perot interferometer has mirror intensity reflectivity R, separation L, and negligible absorption. I'll read all of these. A through E, derive the Airy transmission function, find the free spectral range, derive the finesse in the high reflectivity limit, determine the cavity line width, and explain how finite mirror absorption changes the peak transmission. I kept this rather brief in the answers. So the round trip phase is delta, pardon me for that horribly drawn delta. Delta is equal to 4 pi L over lambda. The Airy transmission is here. That's equal to 1 over 1 plus f sine squared of delta over 2, where that f is, capital F, is equal to 4r over 1 minus r squared. And the free spectral range is that delta nu sub FSR equals C over 2L. For high reflectivity, we have it equal to pi times the square root of r over 1 minus r. And the line width here again, that's going to be, that's equal to delta nu sub FSR over r script f, or Fourier. And with absorption, peak transmission becomes less than unity because not all incident energy exists through the second mirror. Okay. All right. And I'll just leave that as a script F. I'll just call it script F. In this situation, sorry about that. Number 5, moving along. Okay, number 5, a Gaussian beam given this wavelength and waist located at z equals 0. I'll read A through D. So derive those expressions for the waist for r of z and the GUI phase. Thin lens of focal length f is placed at that z equals z sub 1. Use the complex beam parameter q to find the new waist location and waist size. Determine the condition for tight focusing. Explain why arbitrarily small waists are forbidden in the paraaxial approximation. So this is a Gaussian beam propagation problem. So the standard Gaussian beam quantities are this: z sub r equals pi waist naught squared over lambda. And that waist function, waist of z equals that waist naught or beam radius times square root of 1 plus z over z sub r squared. We get here r of z equals that following amount. Psi of z equals that inverse tan of the z over z sub r. And the complex beam parameter is q equals z plus I z sub r. And through a lens, we get this q positive equals that q minus over 1 minus q minus over f. Then propagate after the lens using that q of z equals q plus z. New waste occurs when your RE of q is 0. So the new Rayleigh range is z sub r prime equals Im of that q waste times q waste there. And that waste prime not, that's equal to the square root of lambda z prime r over pi. So we could say tight focusing requires a large numerical aperture and a small input beam waste relative to the lens focal length. However, the paraxial approximation requires small propagation angles, so extremely small wastes violate the approximation. And pardon me if I mispronounced anything so far, just going through this quickly. Let's see. Okay. Number 6, an object has transmission function given here. The t of xy is 1 plus m cosine of 2 pi f naught x, where 0 is less than m is less than 1. It is placed in the frontal focal plane of a lens of focal length capital F. I'll read these through, A, B, C, D. Find the field distribution in the back focal plane. A small opaque stop blocks the zero order component. Find the image plane intensity. C, a second filter passes only the zero order and one first order. Describe the resulting image. And D, explain the physical meaning of spatial frequency filtering. So this is Fourier optics and the spatial filtering problem. So we're going to use this, what we're given here, that t of xy. And we're going to write the cosine as cosine of 2 pi f naught x equals, complex form here, 1/2 quantity times the quantity e to the I 2 pi f naught x plus e to the negative I 2 pi f naught x. So the Fourier spectrum contains 3 orders. T of f sub x, f sub y equals delta f sub x delta f of y plus m over 2 delta quantity f sub x minus f sub x minus f naught delta f sub y plus m over 2 delta sum of f sub x f naught delta f sub y. So here the back focal plane of the lens contains those spatial frequency components. If the zero order is blocked, the remaining field is proportional to that m squared cosine squared 2 pi f naught x. If only the zero order and one first order pass, the image becomes asymmetric and contains a complex exponential interference term. The result is not the original real cosine contrast, but a phase shifted one-sided reconstruction. And spatial filtering means modifying an image by selectively removing or transmitting spatial frequencies. So the last few components of that was more canonical textbook stuff, but very important still, very important. Number 7. Whoops, sorry. Number 7 here. Okay, a rectangular aperture has width A and height B. I'll read through A, B, C, D, and E. A, B, C, D. Derive the Fraunhofer diffraction intensity pattern. Determine the angular positions of the first zeros. Compare the result with a circular aperture and radius A. Explain the origin of the area disk and the Rayleigh criterion. So Fraunhofer diffraction problem for a rectangular aperture. We're going to get this piecewise. A of xy equals defined from absolute value of x is less than a over 2, comma, absolute value of y is less than b over 2, and otherwise it's defined that output is 0. Okay, here the Fraunhofer pattern is proportional to the Fourier transform, so u of parentheses theta sub x, theta sub y is proportional to ab, sync pi a, that's what I call it, just to, some people don't call it that, so for the sake of brevity, I just call it sinc. Pi a sine theta sub x over lambda sinc pi b sine theta sub y over lambda. Yeah, so I proportional to sine squared of pi a sine theta sub x over lambda sinc squared pi b sine theta sub y over lambda. And the first zeros are going to occur at sine theta sub x equals plus or minus lambda over a, sine theta sub y equals plus or minus lambda over b. For a circular aperture, I of theta is proportional to this, to j sub 1 ka sine theta over ka sine theta, that whole quantity raised to the second power. And the first zero gives the area disk angular radius. Theta is approximately 1.22 lambda over d. Okay, so that's number 7. Moving along to number 8. Okay, monochromatic plane. Wave illuminates a straight edge. I'll read through A, B, C, D. Write the Fresnel diffraction integral for the field beyond the edge. Express the result in terms of Fresnel integrals. Explain the oscillatory intensity behavior near the geometric shadow boundary. Discuss the transition from Fresnel to Fraunhofer diffraction. So the Fresnel diffraction problem. So for a straight edge, the field could be written using Fresnel integrals. U of p proportional to this integral from u naught to infinity e to the I pi mu squared over 2 du. And here, define the c u equals from 0 to u cosine pi s squared over 2 ds s of u from 0 to u sine of pi s squared over 2 ds. Then the field is expressed using c of u, s of u. Near the shadow boundary, the intensity oscillates because secondary wavelengths interfere constructively and destructively. The Fraunhofer limit occurs when the observation distance is large enough that quadratic phase variations across the aperture become negligible except as Fourier transform phase factors. Okay, so my apologies if I said that too quickly and mispronounced anything. Okay, so moving forward, number 9. Again, we're trying to just get this quickly. You have a reference. Number 9, a coherent imaging system has pupil function P, K sub x, K sub y, A, B, C, D. Derive the coherent amplitude transfer function, compare coherent and incoherent image formation. Derive the optical transfer function for incoherent imaging in terms of the pupil autocorrelation, and D. Explain why current imaging is more sensitive to phase errors. Okay, so image formation, coherent transfer. For coherent imaging, use of I of xy equals what we have here, the inverse Fourier transform of that P of K sub x, K sub y, Fourier of u sub naught xy closed. So the coherent amplitude transfer function is just h sub c, k sub x, k sub y equals p of k sub x, k sub y. And some would call this f script, by the way. You probably, well, preach it to the choir here. Everyone probably, already knows this stuff anyway. So the coherent amplitude transfer function is just this h sub c, k sub x, k sub y equals p of k sub x, k sub y. And we have here for the coherent imaging intensities convolve with intensity point spread function I sub lowercase I equals I naught star h sub capital I. And the incoherent optical transfer function is this OTF of delta k sub x, delta k sub y, proportional to that double integral p of k sub x, k sub y, p star, k sub x plus delta k sub x, k sub y plus delta k sub y, d k sub x, d k sub y. Okay, sorry for that. And thus, the incoherent OTF is the autocorrelation of the pupil. Coherent imaging is more sensitive to phase errors because phase errors directly affect the complex field before intensity is formed. Okay, so that's number 9. Let's move along to number 10. My apologies if I went too fast and mispronounced anything. I'm on autopilot right now. Okay, so number 10, starting from Maxwell's equations in a source-free linear homogeneous dielectric, A, B, C, D, E, derive the electromagnetic wave equation, show that plane waves are transverse, derive the relation between electric and magnetic field amplitudes, derive the time average Poynting vector, discuss how dispersion modifies the relation between phase velocity and group velocity. So electromagnetic theory of light. Okay, a lot of this is textbook stuff, these relations between, with the notation. And in a source-free dielectric, del dot E is 0, del dot B is 0. Del cross E is that negative partial B dt, dB dt, and del cross B is mu epsilon partial dE with respect to t. If we take the curl of Faraday's law, that del cross E equals that negative partial d dt of that cross product of del and the magnetic field B, and using del cross, the cross product of del and E, that equals del dot E minus del squared E, and del dot E equals 0. So we have del squared E equals mu epsilon, second derivative partial here, E with respect to t. So our V equals 1 over square root of mu epsilon for a plane wave, or E equals E naught, e to the I, k dot r minus omega t. Okay. The condition del dot E equals 0 gives k dot E naught equals 0, so light is transverse. Magnetic field satisfies B equals 1 over omega k cross E. Time average Poynting vector, that's equal to 1 over 2 mu RE cross of E and B star, cross product of E and B star, and a dispersive medium V sub P equals omega over K, V sub G equals d omega dk. So generally V sub G cannot equal B. So generally V sub G cannot equal V sub P. Okay, so that takes care of number 10. Moving along to number 11. Okay, so 11, a horizontally polarized beam passes through a quarter wave plate with fast axis at 45 degrees, followed by a half wave plate with fast axis at angle theta, followed by a linear polarizer at angle phi. ABCD, compute the output Jones vector before the polarizer, find the transmitted intensity after the polarizer, determine values of theta and phi that maximize transmission, interpret the result physically in the Poincare sphere. So, horizontal input, E sub in, 1, 0. A quarter wave plate at 45 degrees converts horizontal polarization into circular polarization up to an overall phase. E sub 1 approximates that 1 over square root of 2, 1i there. Okay, vector. And here a half wave plate rotates linear polarization states, but for circular polarization, it reverses handedness and adds an angle-dependent phase. E sub 2 approximates 1 over root 2. E to the negative I 2 theta over I, E to the I 2 theta. Polarizer at angle phi projects onto here. This is going to equal that vector cosine phi of sine phi, cosine c, cosine phi, sine phi. Transmitted intensity, that's going to be that magnitude there of P transpose E sub 2, that quantity squared. Okay, So since the state remains circular after the half-wave plate, an ideal linear polarizer transmits half the intensity, I equals I naught over 2, and so the transmission is independent of phi. Physically, circular polarization has equal projection onto every linear polarization axis. Okay, so that takes care of number 11. Number 12. Okay. Number 12, two components A and B. A uniaxial crystal has ordinary and extraordinary indices N naught and N sub E. A plane wave enters the crystal at angle theta relative to the optic axis. Okay, A and B. Derive the effect of extraordinary refractive index and explain double refraction. Okay, so this is textbook stuff. Canonical, very important though. Crystal optics problem for a uniaxial crystal, 1 over n sub e squared of theta equals cosine squared theta over n sub e squared plus sine squared theta over n naught squared. And therefore n sub e of theta, that's going to equal this quantity cosine squared theta over n sub e squared plus sine squared over n naught squared raised to the negative 1/2. So the ordinary wave sees n naught. The extraordinary wave sees an angle-dependent refractive index. This causes double refraction. So that's number 12. Okay, moving along to 13. Okay, 13, a quasi-monochromatic source has a Lorentzian spectrum centered at omega naught with line width delta omega. Derive the first order temporal coherence function, find the coherence time, find the coherence length, relate the result to Michelson interferometer fringe visibility. So this is more textbook stuff. Important though, coherence theory. A Lorentzian spectrum has this form. S of omega is proportional to 1 over omega minus omega naught squared plus delta omega over 2 squared. The first order coherence function is the normalized Fourier transform of the spectrum. So we get this is equal to e to the negative I omega naught tau e to the negative delta omega magnitude of tau, that's a tau, sorry, over 2. Thus, the coherence time is approximately this. Tau sub c is approximately 2 over delta omega. The coherence length is L sub c, approximates c, t sub c. That equals 2c over delta omega. In a Michelson interferometer, fringe visibility is V equals this temporal coherence function's magnitude, first temporal coherence function's magnitude, and so the visibility decays exponentially with delay. Okay, so that's number 13. Let's move along to number 14. Sorry. Okay, 14, a step index fiber has core index n sub 1, cladding index n sub 2, and core radius A, B, C, D, E. Derive the numerical aperture, define the normalized frequency, determine the single mode condition, estimate the number of guided modes for V is much larger than 1, explain qualitatively how bending loss arises. So guided waves in fiber optics. Okay, for a step index fiber, NA equals square root of n sub 1 squared minus n sub 2 squared. The normalized frequency, that's 2 pi A over lambda NA. The single mode condition for a step index fiber is the normalized frequency here less than 2.405. Okay, and for a large normalized frequency, the approximate number of guided modes is M approximates that value squared over 2. And bending loss occurs because bending shifts part of the mode field toward the cladding, allowing energy to radiate away instead of remaining guided. So that's a number 14. Moving along to 15. And this is textbook notes stuff, important. All of it is important. 15, a singlet lens is used to focus a collimated beam. Let me read through A, B, C, D. Explain spherical aberration, astigmatism, field curvature, and chromatic aberration using third order aberration theory. Qualitatively explain why aperture size strongly affects image quality. Discuss how achromatic doublets reduce chromatic aberration. And explain why asphoric surfaces improve focusing. Okay, so optical elements and aberrations. Spherical aberration, rays far from the optical axis focus at a different point than periaxial rays. Off-axis point, sources from comet-like images. Astigmatism, the best image surface is curved rather than flat. Chromatic aberration, different wavelengths focus at different distances because n equals n of lambda. Aberrations grow strongly with aperture size because marginal rays sample more strongly curved parts of the lens. Achromatic doublets reduce chromatic aberration by combining positive and negative lenses with different dispersions. Aspheric lenses improve focusing because they correct the surface profiles, so marginal and periaxial rays focus closer to the same point. So this was more textbook stuff for 15, conceptual textbook stuff. 16. In 16, we have a weak optical field is incident on a photodetector with quantum efficiency eta. For a coherent state with this photon number n bar, derive the photon counting probability distribution. B, find the mean and variance of the detected counts. Compare with thermal light. Explain photon anti-bunching and why it cannot occur for classical light. So this is a photon statistics and detection problem here. So for a coherent state, we get this is equal to E negative n bar to the n over n factorial. With detector quantum efficiency eta, the detected mean count is n bar, so D equals eta n bar. Thus, we have this is going to be equal to E to the negative eta n bar eta times quantity eta n bar to the m over m factorial. And the mean and variance are right there, that average m, okay, or expected value of m, that average of m, and variance of m equals eta n bar. For the thermal light, we're going to get, that's going to be equal to n bar to the n over 1 plus n bar to the n plus 1, and our variance of n bar plus n bar squared. Thermal light is bunched, coherent light is Poissonian, and anti-bunched light satisfies that second order G of 0 is less than 1. So classical fields cannot produce true anti-bunching. Okay, so that takes care of that one there. Okay. 17, pardon me if I mispronounce anything, just going fast. 17, a plane wave at frequency propagates through a chi second nonlinear crystal. Derive that driven A, B, C, D, E. Derive the driven wave equation for the second harmonic field. Define the phase mismatch delta K. Derive the dependence of second harmonic intensity on crystal length. Explain the coherence length. Explain quasi-phase matching. So this is non-linear optics harmonic generation. Okay, so in a Chi2 medium, that P2 of 2 omega here, E naught Chi2 E sub omega squared. The second harmonic wave equation is this, okay? This del squared E sub 2 omega minus n squared sub 2 omega over c squared. Second derivative here of partial E sub 2 omega with respect to t equals that mu naught second derivative here with respect to the P2 with respect to time. Okay, so moving forward here, the plane mismatch is delta K is K sub 2 omega minus 2 K sub omega sub 2 K sub omega. The second harmonic intensity scales is I sub 2 omega proportional to I sub omega squared L squared sinc squared of delta KL over 2. The coherence length is L sub C equals pi over magnitude of delta K. Quasi-phase matching periodically reverses the sign of the nonlinear coefficient, so the generated second harmonic field continues to build constructively. Okay, so that's number 17, textbook. A lot of it's textbook stuff. This is also a lot of textbook conceptual stuff for 18, and this is the last one. Okay, so we have a medium has nonlinear refractive index n equals n naught plus n sub 2i. Explain how a Gaussian ABCD. Explain how a Gaussian beam produces a nonlinear lens. Derive the qualitative condition for self-focusing. Define the critical power for self-focusing. Discuss how group velocity dispersion and self-phase modulation combine in ultrafast pulse propagation. So, nonlinear optics, Kerr effect, and self-focusing. The nonlinear refracting index is n equals n naught plus n sub 2i. For a Gaussian beam, we have this I of r equals I naught e to the negative 2r squared over the waist squared. So the index is largest on the axis, n of r equals n naught plus n sub 2i naught e to the negative 2r squared over the waist squared, or beam radius squared. If n sub 2 is greater than 0, the beam induces a positive lens. This can overcome diffraction and cause self-focusing. The critical power has the approximate form P sub CR is approximately lambda squared over n naught n sub 2 with a numerical prefactor depending on beam shape. And self-phase modulation arises because intensity-dependent phase is phi sub nl equals k naught n sub 2 il. For ultrafast pulses, group velocity dispersion changes pulse duration while self-phase modulation changes spectral bandwidth. Their balance can produce soliton-like propagation in suitable media. Okay, so that's all 18 practice problems in modern optics, and hopefully this could be of assistance to give you extra practice or just for some fun doing some problems. Okay, thank you very much and have a great day.